So this is Statistical Rethinking, second edition, chapter 15. And we're just starting the hard problems. And so we're going to look at 15H1 and 15H2 together because they're, they piggyback off one another. So we're looking at a data set called elephants, and it's counting how many different matings bull elephants have had, as well as their ages. Okay, and we're going to fit a Poisson model to it, and then my cats are going nuts over there. And then we're going to add some measurement error to age. Okay, so we're predicting matings with age, and then we're going to add some error to age. And then in 15H2, we're going to add as much error as we need to cause the coefficient for age to go to 0. Okay, so here's the data set right here. Very simple, right? The age of the elephant and the matings, okay? And so I've ran all of this stuff before, so there's going to be a lot of junk around. Hide that, okay? So, the first thing that I'm going to do is I'm going to subtract 10 from the age. This is not exactly arbitrary, but it occurred to me that elephants aren't mating at 0, 1. They have to reach sexual maturity before they're mating, I assume. And so a quick Google search said that they tend to hit sexual maturity between 10 and 17. So I'm just taking 10 here. Okay. So here's the model that I'm using. Okay. So we have a Poisson model, and we're used to taking the log of lambda, but the log of lambda is the same as exponentiating your linear model here. Okay, and so I don't have an intercept. Okay, and the reason is because I assume that at sexual maturity there's 0 matings or very close to 0 matings at 10 years old. So I don't have an intercept here, but I do have this offset here. And the reason that this offset is here, well, you can do some plotting, but it helps to make sure that that the exponentiated plot here starts at 0. Okay, basically. So that's neither here nor there. You could run it without it, and it actually runs better if you do it without it. But anyway, so when you run it as is, it'll run just fine, but you will notice that it throws a bunch of warnings. And so to make sure that the model converged, I not only looked at the R hat, but I also looked at the trace and trank plots, and these look fine. So it's kind of weird dimensions here, unfortunately, how it renders here in Colab, but these look fine. You can see that all the estimates converge pretty quickly, and so that's good. And so now to plot it, you can look at the code to see how this all pans out, but this is the plot of age minus 10, but of age since sexual maturity and matings, right? And I mean, I don't know, to my eye that looks decent. So we got that. Okay. Well, the next thing that we're going to do is to add measurement error. Okay. And see what happens to the model, to the coefficient estimate, to the posterior distribution, etc. So in order to add the measurement error, so look at the code here. Now, I actually, if you struggled with this, I actually had to play around with this a lot to get it to work. And what I ultimately learned was that you had to have these things in the correct order, right? So you had to have, I'll go through the code here in a second, but you had to have these things in the right order. If I had the prior for B up here, it would not run. I mean, the model was throwing errors. And one of the frustrating things about the Rethinking package, is fantastic as it is, even when I'm doing normal work, I often use Rethinking because it easily expresses your model to other people who don't, maybe not be able to read Stan, for instance. when there is an error, remember a rethinking is passing your model to Stan, and so the errors come from Stan, and Stan uses a different syntax, right? And so sometimes it's hard to understand what the error is. But ultimately, that's what I determined, was you had to have these in the right order. Okay, so what's going on here? So we have the exact same model, but now instead of age, I have age true, okay? And why age true? Well, because we never observed age true, we observed age measured, okay? Which I'm defining down here in the data list, okay? And we're saying that age measured is the true age plus some error here, measurement error, okay? So that's what's happening, right? So that's where we're getting true here, age true. Well, that's how the model's working, and you can just kind of see how the rest gets filled out to make to make the model run. Okay, so this runs, and again you get all sorts of warnings. I'm just going to hide this just for easier navigation. And so again, I look at the trace plots and the trank plots, and and all of these coefficients, they all come out to 1. So all of that looks just fine. So let me hide that. In fact, while I'm at it, why not hide this guy? Okay. All right. So I'm going to go through and I'm going to plot this on top of the pre-existing plot. So the pre-existing plot is the bottom layer here, or the bottom line and credibility interval, and red, the red dotted line, is our estimates with the standard error. And it basically looks identical. The lines are more or less plotted directly on top of each other. If anything, the standard error is a little bit wider, of course, but that's fine. Okay. So there's not much difference. So that's the end of 15H1, and now in 15H2 we are supposed to increase the the measurement error to try to, and well, it says to drive the coefficient towards 0, but just a spoiler, that doesn't happen here. But so let's change the error by a standard of magnitude. So here 50. So this is the exact same model that we used before. Okay, same model, but I've just changed the the standard error for the measured age to 50. Okay, so, and it was 5. Okay, so let me hide this. Okay, again, this runs just fine. Hiding all of this stuff. Okay, and so now I'm going to, basically just duplicate the same code, and now I have the 3 plots going. Okay, so now the blue, let me zoom in on this. The blue here represents, this standard error of 50 data, okay? And it doesn't really shift that much. I mean, like, it certainly isn't driving towards 0, okay? So if anything, our line is actually moving up, so the coefficient is moving up, and just barely, maybe negligibly, but we do see that there is more margin of error, or greater error in the predictions here. So, okay, so that's interesting. So what if we went up another order of magnitude? So now we'll try an error of 500. Okay, so we run that. Again, everything runs just fine. Just hiding that. And now we plot it, and now so I'm plotting this guy in green. Let's open it up over here. And again, this line is basically plotted right on top of the standard error of 50 line, and now the standard error is greater or whatever. But the coefficient for B is never driving towards 0, right? And we can actually see that if we look at the pricey outputs for each of these, right? So here they are for the 4 models, and they're basically the same. Okay, well, why are they basically the same, even though the question kind of led us to believe that they should be, that the coefficient should be diminishing? Why is that not happening? Well, it's because when we are adding this error, we're adding the same amount of measurement error to each observation, right? So so there is still signal there, and so and the model is just simply picking up on the signal. That's what's happening. So just because we added error, we added the same amount of error to everything, and so the signal you know, remains, it remains maybe with a little bit lower fidelity, okay? So, so anyway, that's what's happening there. All right, so we'll call that good.